Hello, math nerds. If you enjoy calculus and seeing how it's applied in a particular mode, you might enjoy this video. If you've never had calculus and you don't have an interest, you might not want to watch. It's gonna get ugly. Well, it's not ugly. It's kind of pretty. But this is called integrated rate laws. So if I think back to our description of how a rate of a reaction can perhaps depend on some reactant to the first power, including a constant. Here I just use smiley face to represent something, some kind of species of chemical reactant, could even be a product, but I'm just lazy and don't want to leave it blank, and I don't want to write the formula either, so C whatever, H whatever, O whatever, N whatever, I don't care, just call it some compound. And we happen to know from previous experiments that it's first order. Remember, the square brackets always mean molarity, so when you see that, it means moles per liter, and that's probably aqueous, although it doesn't have to be aqueous. It could be a gas or some other composition, but yeah. All right, so let's go from here. So if you're familiar with the language of calculus, let's say this: the rate of change of my species is equal to some constant times that constant's concentration to the first power. Let's imagine what happens is we change a little bit. Well, actually the definition of rate of change is the change in concentration versus the change in time, or incrementally, little teeny change in the concentration compared to little teeny change in time, shrinking the time to as small as possible. We just stick a negative in front to say that it's decreasing. Alright, so what? Let me do a little bit of algebra with this. Let me take just take this one right here. Ignore that. I want to go with the incremental change, negative d smiley by dt. So I rewrote that. And let me shift the negative to the other side, just for the sake of entertainment purposes. Multiply both sides by negative. And now a trick. Let me go ahead and put the time component over here with the constant. And let me put the smiley concentration to the first in the denominator over here with the other d smiley. Interesting. Now I have the left-hand side with regards to time and the right-hand side with regards to smiley. Let me add things up. Let me integrate both sides. So let me add up the constant. That's going to be able to shift out front. dt, there's nothing inside. And no other time function, it's just a constant. And on this side we have the integration of d smiley over smiley concentration. So let me show you what that could look like. So the time, I'm going to go from 0 to t, sometime t. And the concentration of smiley will go from 0 in the beginning, original, to sometime t. That's the concentration of smiley at some later time t, and this time matches with this time, and this 0 time matches with this original as well. Isn't that interesting? So if you know anything about evaluating integrals, you know this is pretty simple, and you know this is also pretty simple. Oh, yeah. The antiderivative of that comes out to the natural logarithm. So if I take the derivative of that, I go backwards to here. If I take the derivative of this, I go backwards to here. And we're evaluating again at 0 and t, and at 0 and t. So t minus 0, and the natural log of the smiley at time t minus the natural log of smiley in the beginning originally. And I'm basically there. In other words, another property of logarithms is this logarithm minus this logarithm is the logarithm of the division of this and this. So here's a common way we'll see that integrated rate law written. Another common way, if I want to get rid of the natural logarithm, I take e to the x, e to the power here, and e to the power here. E to the power here cancels the logarithm, and I just have that division, that ratio. Or, if I wanted to rearrange this, I can also write it this way. This is a very useful form because it allows me to see the mathematical graphing connection between the concentration of smiley at a certain time and the original concentration of smiley via some linear relationship. So I would remember this one, practice it a lot. These are variations that are also on occasion nice. But if I were to make a graph, on the y-axis I put the natural log of smiley at particular time. So that's a function of time. And here's the time over here, some constant. And the y-intercept ends up being the natural log of the smiley original. Isn't that crazy? In other words, that's y equals mx plus b. This is the y-intercept. Oops. Sorry about that. So look at that relationship. See if it makes any sense. Then the slope is the negative constant. So there's the slope of the line right there. Another common question we will ask is, what's the half-life of the reaction? The half-life occurs when the concentration at a particular time drops to 1/2 the original concentration. So if I go back to my integrated result and plug in for the half-life time, the time of half-life, that's given. That's what we just derived that. But I want this smiley at t to be equal to 1/2 the original smiley. So the smiley originals cancel, and the natural log of 1/2 is a constant number, negative 0.693. And I solve for the t 1/2, and it seems like that the half-life is a fairly simple equation for a first-order decay. It's really simple because this constant doesn't change and this doesn't change, and so the half-life doesn't change over time. The half-life remains the same from period to period as time goes by, which is not the same as a second-order integration. This is also interesting. The final result's a little bit trickier, but not much, just different. So the rate of change of smiley is to the second power, second-order rate law. And that's what it means. So in a way very similar to what we just did, where we consider the change in smiley over change in time, shrinking that to a very, very small time frame, d smiley by dt, negative because it's decreasing, second power. Let's see. Shift the negative from here over to here, and then let me do that mathematical trick of moving the time dt over with the constant and the smiley squared from the numerator here to the denominator over here. Just a little bit of algebra. Now the calculus. Let me integrate both sides. The constant comes out front of the integral, nothing inside, just dt, and the integral of this over d smiley. Is that stupid or what? Stupid calling it smiley, but it's simple to label it that way. Integrate from 0 to time, integrate some time t, integrate from the original concentration to some concentration at t. Then, let me rephrase that. This left-hand side's the same, but let me call that smiley to the negative 2 because it's in the denominator. Anti-differentiating that to evaluate smiley to the negative 1 from 0, concentration at 0, concentration at time 0, time t, t minus 0. And this is the smiley to the negative 1 at particular time minus the smiley to the negative 1 at the original concentration. And there we basically have it. The way to say that, which is a common way to say that, yeah. You'll want to remember that, or at least practice it enough you can pull it up to mind really quickly. And this is a similar, oh shoot, maybe I should have rewritten that. I can write 1 over smiley at t equals kt minus, kt plus 1 over smiley original. And that equation always ends up looking like this, where I put the smiley on the y-axis as a function of time, and the slope is a positive slope in this case, and the intercept is 1 over smiley, the reciprocal of smiley at the original time. Or phrasing that in the language of linearity, y equals mx plus b. Y, m, x is the x-axis, t, and b is the intercept. We might also take the time to think about the half-life of a second-order reaction. Same definition, the concentration at the half-life time drops to 1/2 the original concentration. From my above derived equation, I take this, Oh, I rearranged it. I put this on the other side and the KT over here, or vice versa. And let me fill in for the T half-life. The time, let's see. Oh, I know what I'll do. Instead of this half-life time concentration, let me put in 1/2 the original concentration, which is the definition of half-life. And now I have a common term here and here. Let me get those together. Oh, I see what I did. I took that 1/2 up to took the 2 upstairs. Then let me get those two terms together. Bring this term over to this term. And that's 1 over Smiley original minus, 2 over Smiley original minus 1 over Smiley original gives 1 over Smiley original. And my final answer is my half-life time is actually a function of the original concentration. So this is kind of weird. The half-life time for a second order decay or reaction is not constant. It changes, and it actually, let's see, as this goes down and down and down, then this goes up and up and up. It takes longer to decay, which is kind of an interesting idea. Constant K, slope of the line, original concentration, or concentration at a particular time. Whew, my goodness. Let that soak in. Thanks, guys. I'll practice that more later.